Good afternoon, everyone. Let's get started. Welcome to our second faculty seminar of the semester. Really appreciate you being here, taking the time to do this. Excellent turnout. I'm excited about Marcos's presentation today. So Marcos's talk is going to be on digital ag at the large scale using current data sets and tools to address emerging landscape challenges. Sorry, I should have introduced myself. For those of you that don't know me, I'm Rob Duncan, professor in plant science and associate dean research in the Faculty of Agricultural and Food Sciences. So my pleasure to have Dr. Cordeiro here today, and I'll start off with a little brief bio for Marcos. Marcos is an associate professor in animal science, and his background is in biosystems engineering, which I did not know, focused on statistical and mathematical modeling of agroecosystems with emphasis on both crop and animal production. Marcos is skilled in spatial analysis using digital data sets as well as development of analysis workflows for large data sets using high performance computing systems. His current research is on beef production, including mapping of grassland resources, using advanced spatial analysis techniques, simulating grassland productivity with high resolution, hyperspectral, and LiDAR data sets, using drones, and modeling hydrology and nutrient dynamics in pasture landscapes with limited data. Additionally, Marcos explores the impact of beef production on biodiversity through ecological modeling and simulates large-scale carbon dynamics. He's also engaged in sensor technology development to create key performance indicators for dairy cattle. So with that, let's welcome Marcos.
Thank you, Rob. Thank you, everyone, for coming. It's great to have a captive audience for a few minutes and to have the opportunity to talk about what we do and reflect on this and give some perspective to the work that we do to ourselves. So I'd like to start with the acknowledgement that the University of Manitoba campuses are located in the original lands of the Anishinaabe, Cree, Oji Cree, Dakota, Dene people, as well as homeland for the Métis Nations. We respect the treaties that were made in those territories. We acknowledge the harm and mistakes of the past, and we dictate ourselves to move forward in partnership with indigenous communities in a spirit of reconciliation and collaboration. For this talk, we're talking about digital ag, and I've been for a long time thinking about this new field from a teaching perspective and a research perspective, which is sort of new, and some people have a hard time even defining digital agriculture, right, what it is. It can be different things for different people. And I think the problem is because you're in the period of such a fast development, you're so close within the development, it's hard for us to define, right? And this is the perspective that some other people have realized for other fields as well. In this example we have here for, this book talks about statistics, and they talk about how statistics was developed in the later 1800s. Through individual efforts, they were disconnected and chaotic at the time, and didn't seem to make much sense. But when you take a step back and start looking 100 years later, you start seeing some trends emerging that is not as noisy anymore because you're looking from farther distance, right? So with that, with this contrast, what I'd like to highlight here is that the perspective depends on the scale that you're looking at, right? Sometimes they're too involved, too close to realize that, the big picture. But when you have the time or the space to look at distance, you realize trends that you don't see before. And this is where I want to capitalize, right? I want to think about the question of scales in agriculture, because far too often you tend to think that things are static, they don't change. And you know that the only constant is a change, as people say. So we know this when you talk about climate, but this is also true when you talk about space as well. So my challenge for us today is to look at different scales, and this is the take I took in my research, is looking at large scales to look at what they have in particular and what kind of trend we can grasp from that, right? So large scales, and there's not one scale. I'm talking here about space and time, so two scales. There could be more. they come with challenges, and they come with some tools to address those challenges. And the challenge that you have that's not particular to large scales is the challenge of measuring everywhere and measuring all the time. And this challenge is not new only to large scales, because at the farm scale, you have the same challenge. You don't measure as much as you'd like to. But for the large scale, this is more emphasized, this type of challenge. And we use some tools to address that. And the first one of them, which is logical, is to measure more, right? You want to measure, get more data to address this challenge. And we have made huge strides on this little bullet here, because in the last 10 or 15 years, there's been just a deluge of data sets that you can use now that is making our life way easier. We also rely on more sensors. So a lot of this data is coming from new sensors. So this is another term for digital ag, lots of sensors in tractors, in fields, in soils, as well as weather stations. So as you move into the scales, we have those sensors as well. But you also try to use the models, which are those black boxes, sometimes gray boxes, that we use to fill the blanks, right? To know about the challenge that you cannot measure, but how can you estimate that? And one big piece that book talks about is the creative spirit that leads to development of methods, right? Sometimes it's the brand new method that you can develop. This is because you're dealing with new data that requires new approaches to it. But in many cases, just dealing with application of old methods with a new phase, so to speak, to apply to new problems. So through my presentation, I hope I will cover some of that. You can see some of those challenges and tools exemplified here. Okay? So I'm going to talk about 6 different projects that we are currently working on. And they can be grouped into grasslands, cropping systems. Then the second bullet here, you have more of annual crops. And then later on, we talk about biodiversity and more of environmental studies, even though we have environment going through all the teams here. And yeah, so this is going to be a very high level. I didn't want you to change this into a data dump, but just to give you the taste of what we're trying to do at those scales. So the first one is simulation of grasslands and looking at the impact of climate change in those landscapes. This is important because those landscapes are important for economic activities in the prairies, like beef production, but also because of ecosystem services, like carbon regulation and air quality, for example. So the idea for us is, the question for us was, is climate change going to impact productivity? Because those services depend on the productivity of the biomass production of those landscapes. Here we face the challenge of not being able to simulate across the prairies. So what we did is we took representative areas from each province to try to simulate what happens there and hopefully extrapolate to a larger space. So we have 3 watersheds in Manitoba, Saskatchewan, and Alberta. And as you can tell by the scale bar here, those areas are not huge. That's because it's very hard to find homogeneous area of grassland cover. So you're shooting here for 75% or more cover of grasslands. So it was very hard for us to find pristine areas that you could use for modeling here. And then once you have the baseline model set up, use the IFSM model, which is the Integrated Farm System model developed by USDA. This model was developed to simulate dairy farms and beef systems, and using this on the beef system on the grazing side. So we set up the baseline model of historical conditions, and then you run the models with future climate projections to see what you'd see, right, in terms of forage productivity. So when you look at the climate models themselves, so what you see on the lines here is an average of three atmospheric models with the average and then the 95% confidence limit there. And this is not very different than what you see across Canada, for example. We see this trend in temperature increases. This is RCP 4.5 is a scenario of moderate emissions. RCP 8.5 is a more extreme emission factor. Therefore, you see a more steep increase in temperature there. So for the most part, you see an increase, except for Alberta here, where the trend analysis show no significant trends. So for Alberta, even though it's increasing, here in the near future, not significant, but just for the most part it is. And if you leave the stats aside for a second, there's still an increasing trend that's not significant there. For precipitation, the same picture. You see, for the most part, a moderate increase across the seasons here. What you see is the reference period, near future and distant future, in different colors. So what you see across all the sites and years is that there is a 2 to 7% increase in precipitation. Okay, so it's a moderate precipitation, but this increase only comes during the winter and spring. So this might have a limiting factor on the yields, because what you saw for yields was a 5% more or less increase or decrease compared to historical periods. So you see climate change is not going to drastically impact the productivity that you see in the long term. But remember, this is average weather, okay? Climate projection is simply average weather. So we don't see this on average. What's more relevant to us is what producers experienced a couple years ago with the droughts. So extreme events become more relevant to us. So on average, this might not be very significant. The next step for this work will be looking at the extremes and seeing how this works. What's also interesting for us is see how temperature increase, which leads you to think that we could have an increase in productivity, is not playing out because you can have a drought during the summer. So we're also trying to look into this relationship and interplay between weather variables to see if productivity is going to increase or not. So the second study, still dealing with grasslands, is confined to Manitoba, but it's much more data intensive because you're doing a continuous surface across the agro region of the province. So the reason for this study was motivated by the Manitoba Protein Advantage Strategy, which aims to get a 15% increase in protein production in the province. And this includes animal protein, which includes beef, which depends on grass. Therefore, we use this. This is also important because the province administers the Crown Land Program, which leases lands for producers. So the productivity of those lands is crucial for them to set up the price properly and to also make sure that they are asking or charging for what's reasonable and expected. So this is the motivation for this. So what we did in this study was we started with a product that the province has called Manitoba Grassland Inventory, which is a raster classification of the grasslands. And then we found some forage yield scattered across the province and tried to extrapolate from those points across all the province. So we estimate the stocking rates and we extrapolate by assignments based on weather properties. This was a rather convoluted process I don't have time to describe here. It was a hierarchical 6-step approach going from more precise to more uncertain. But at the end of the day, we get carrying capacities, which is stocking rate by area, aggregated by area, and then you could see the status of the grazing across the province. And we compare this to the official records of the province to see is there any potential for improving this or increasing the allocation of those resources. So let me guide through this. This is the graph of carrying capacities for different ecoregions across the province. This is the same data. This is just zoomed in at 40,000 AUM. So, okay, whenever you cannot see this box is too small, look at this here. Okay, it's just a zoomed out version of that. So I'm going to speak mostly to the top box. So the red line is the official records of the province. The black line is our average. We also approach this from an uncertainty standpoint, so we have the ranges. So what you saw is for the region with the highest available carrying capacity, the province is doing quite well. We actually utilizing this resource quite effectively because there was no difference there. Of course, you have to take into account this range here. So productivity varies within this range, but on average, we're not doing too bad. The potential, though, oops, too fast. Let me go back here. The potential comes when with the second largest ecoregion here, which is the parkland area. So as you can see, the province show that we are underutilizing the resource because we have more unused capacity here. So this gap could be bridged if we bring this line up to here. So there's potentially more carrying capacity to be utilized. There's also this one on the Assiniboine Delta, but this one, as you can see, is not as much carrying capacity available as compared to the first two regions. Okay. The other thing that became apparent to us was that for when there was some potential, but not as much because the lines are much closer. They're within the uncertainty range, right? Okay, this is still underutilized, but not to the same extent as those two. And then finally, we have the overgrazed areas, which I want to highlight 2 points here. One, those are forest-dominated regions. So that means it's not grass-dominated, right? So typically, there's not enough feed resource in those areas. Therefore, people tend to overgraze because of the reduction in productivity of forests compared to grasses. The other thing is that those areas are not very expressive compared to other areas. So when you talk about overgrazing and undergrazing, you have to keep this context in mind, right? How much overgrazing in which areas and how much of that is really relevant to us here. The beauty of this study is actually when you show this spatially, because now you can see where these areas are. Okay, so we have undergrazed at negative values here on the map, so that means the darker dots are undergrazed. This is where there's potential to be more explored. And the yellow one is where there's overgrazed, we should do better. So as you can see here, on the interlake plains, there's a lot of red dark dots here. That means we, or the province should, or we should do a better job at utilizing this to its full potential. So by knowing where it is, we can kind of target the areas that could deliver most bang for the buck. Across the province, though, we have about 9% underutilized resource that you could explore. That equates to 58,000 plus AUMs that could be allocated to beef production. So not quite the 15%, but still, right, a good beginning that could start exploring. And this 9% could be further explored if we allowed improved management in those lands, because leased lands, typically producers don't feel that they can explore much better because no incentive. If we can incentivize that, it could improve this 9%, okay? One thing to keep in mind here, though, is that the uncertainty of this, because all this distribution was based on a few data points, 13 data points across the province. So we need to do a better job at collecting data here to be able to improve those estimates. But this is a good beginning to give you the pointers to which direction to follow. The third study on the grassland class is still about productivity and distribution, but this is using a different approach. This is using hyperspectral data and LiDAR data, which is the golden grail is as good as it can get in terms of remote sensing. Because you have way more spatial resolution, because those are drone-mounted sensors. So because you're flying so low, you have way more spatial resolution. Your pixels are really small, as well as increased spectral resolution as well. So the amount of information in each image is much higher. For example, some satellites have 7, 9 bands. Those sensors have hundreds of bands, sometimes close to 500 bands. So there's a lot of information within those sensors. From a methodological perspective, we still use the same approach. You cannot measure everywhere. So we try to select 4 sites for which we have a good range of grassland management and types of grasses. And then we just went out there, flew this drone, collect the samples, and trying to create some statistical models to relate the two and create predictive yield biomass productivity models using this. Prediction models, sorry, I should say. But no, we hear a lot about drones, but not every drone is the same. This is a very special system. It was developed not as a sensor, not as a drone, but as a system as a whole to do exactly what it does, right? High performance. So it's comprised of 3 components. The drone itself, the gimbal, which is the arm that holds the sensor, and the sensor. So this drone is a high-performance drone. It's capable of carrying high payloads. This payload is 25 kilos here. So this is at the edge of what we can fly with a basic license. So they designed it that way. The other component is the gimbal, as I said. The gimbal is used to reduce the vibration on the sensor. So trying not to get all the vibration going down to your image, right? So what it does, as you can see here, the drone will do a fast swing to the right here, and the sensor is supposed to be steady, okay? And the gimbal also records any change in pitch or roll so that this can be corrected later in the image. And of course, the last piece is the sensor itself. As I said, this black box can collect hundreds of bands or different pictures at the same time. and then we try to make sense of that later. However, these many bands create some challenges as well. The first one of them being the processing, the pre-processing, right? This is not data analysis yet, just pre-processing from raw to a data cube. I don't mean for you to read any of that, but just keep track of the blue boxes. This is the amount of the different pieces of software that you have to use from data acquisition all the way to the final product. As you can see in orange, this product is changing its format as it goes along. Besides all the the white boxes, that means different types of inputs that you need to provide. This could be files or different informations. So it's a quite a complex process. They also use expensive software, but because it's a system, we kind of locked in for that. So we have to go with that one. I would much rather prefer using open source. The other challenge that it offers is the curse of multidimensionality, right? So we have too much data to make sense of. So what you do now is to try to use statistical processes to remove the redundant bands in the data set. So we were able to effectively use PCA to reduce from hundreds of bands to only two channels. And those two channels retain 98% of all the variability in the data set. So now it's much more easy to manage and handle the amount of data without losing much of the information. So what we did with that was we tried to compare to create traditional indices that's used for vegetation assessment, like NDVI. This is normalized difference vegetation index. So this is an index that indicates greenness, okay? How much of vegetation is there. So what we did was use this with the optimal data that you got from hyperspectral, the PCAs, and also use standard calculations that people use with satellite imaging, for example. So you already can see here there's some difference in the images, right? This is not an apples to apples comparison because you have to kind of get those scales to the same range. So it's a little bit different. The colors don't mean the same thing in both pictures. But you can already see there's already some differences here. And the red dots are actually the biomass samples. So where the difference really became apparent to us was when we tried to create the prediction models, right, from using the biomass. So you have the biomass weights or from the samples and then the NDVI index. So you can see the improvement as you move from standard to the PCA-based approach. So here already showing some promise for us. We're still analyzing the data from 2025. So hopefully you get a better improvement of this, but this is already improvement by using more detailed data here, okay? And the next step on this is scaling, right? Because the drone has a limited footprint when you can only fly so far or so long. So the idea for us is to extrapolate from here to the large scale. And we got a grant approved by the space agency in Germany because they have a hyperspectral satellite. So the idea for us is to get this imagery and be able to get the models developed here and apply it to the broad landscape. So in that way, you can estimate productivity to larger areas. And this, again, has lots of applications, not only for beef producers, but for ecosystem services as well. With that, I'd like to move to the second group of studies we're going to discuss, which is cropping systems. So here now to bring annual cropping in. And I'd like to highlight here that this study I'm going to discuss is part of the NSERC SARI grant that was awarded to the University of Manitoba in partnership with USask and a number of partners from the industry. So this project was led by Martin Ents before his retirement. Now Joan is leading the charge. And we call this the LEAP project. This is, try to explore ways to move very fast towards net zero. So we exploring a number of fronts. This project is very innovative because it tries to do a participatory approach with farmers as well as First Nations. So trying to integrate their perspective as you try to come up with our net zero possibilities, right, for the cropping systems in the prairies. There's also a fair bit of data being collected, biophysical data collected on the landscape analysis on pillar number 3, as well as a lot of work done by Yvonne Lawley on at the plot level with the innovative farming systems. And the idea for us here on pillar 5 is to aggregate this information and be able to translate it into models that you can be used to predict and inform us in terms of what's more effective towards net zero approaches. So coming from the rationale for this is one of many studies that we're conducting right now, is we know that cropping systems are very dynamic, right? So we're trying to track three things here. One is the emissions, the other one is changing soil carbon, the other one is the net zero effect of those two variables, okay? This is easier said than done, very hard to do. But the modeling environment allows us to do this very easily. So what we did was to collect data, weather, and practice of the cropping system for 28 locations. We cannot see 28 here because they overlap on the map. But we have 28 cropping systems here. So we collect weather data and management practices for those 28 farms. Characterize them in terms of weather and management. And because you had 28 by 28, this would be way too much data to model. So again, using a clustering analysis, we did the reduction technique to come up with a smaller number of scenarios to model. And we used the Holos model from AFC, which is a greenhouse gas model, to simulate many of those components that you need. And then we pre-process the data, post-process the data to see what those trends look like. So let me just spend a few minutes here explaining how we did the move from 28 to 8 management systems. First, we try to group them broadly among annual, intermediate, and perennial systems. So annual is a system that only has annual crops. Intermediate has both annual and perennial forages, and perennial is a fully perennial system. So as you can see here, the number of farms varies according to the system, right? But in order to avoid, you don't have three categories in this case. So in order to get more detail, not to lose as much, we also classify this based on the dominant crop within the rotation. So for example, in this annual system here, a cereal is the dominant crop, the rotation, and so forth is intermediate forage, the same idea. Okay? With that, we end up with 8 cropping systems to model. And then we move on to the data. Out of those 28 farms that you had, we try to group them based on climate and based on soil texture. So we can see by the different colors, you have dry, mid, and wet conditions. And within those conditions, you have different soil types. You have coarse, fine, and medium. And we didn't have all the conditions for all the farms. So as you can see, for wet conditions, we didn't have the coarse soil. That was not represented in the 28 farms. So you cannot bring it here. Now that you have characterized or data reduced both the farm systems and the weather, we went on to the simulations into the model, which simulates emissions or losses, and then the gains in the soil in green here. So if you're gaining by sequestering carbon, that means the lower net zero, the better for us. So you want a low net zero index here. So when you put this on a graph, what it looks like is on the x-axis, what you have is your emissions, right? So the lower the better. You want to be closer to the origin here because you want to reduce your emission. When it comes to soil carbon, the higher the better because you want more soil, more carbon in your soil. So ideally, as you can see here, the perennial system is doing better because it has a low emission and a high soil carbon. Okay? And then the color here indicates how close you are to net zero on this scale. So that would be green, close to net zero, or red, not doing so great. So as you can see on the distribution here, perennial forages come number 1. You can also see the rank there because, as I said, no emissions, high soil carbon. And what's interesting for us here, because you're trying to select or at least to propose what's the best management across different conditions, we can look at, for example, this is only for dry soils or for fine soils. We have this for all the soils and conditions. I don't have time to show all of that. But you can see as you move from dry to mid-wet conditions, the rank persists. So the rank is the same. The type of performance of the system is the same. As soon as you get wet conditions, it all collapses, and they all come together, right? Much closer. Forage is still number 1, but it's no longer isolated in terms of performance. And for us, what you want to see here, for example, if you look at the rank number 2, we had an intermediate system with a cereal, and then number 2 becomes a pulse. So when the conditions change, the type of a system that you use might be different. So the idea for us here is not only to identify which system is better under which condition, but also how can I fine-tune this, right? because with an intermediate system, I have an annual crop and I have a forage crop that has both emissions and soil carbon. So how can I improve that management to be able to maximize soil carbon storage while minimizing emissions? Okay? So this is the goal of this study. We're really excited about this. So the next weeks we should dive deeper into this assessment of this and move forward with the dissemination. Okay, the second study under the cropping system is looking at large scales, okay? So now we're looking at setting a model across the Agro-Manitoba region. We use the SWOT model for that. And the idea behind this project is because some of these processes only become apparent when you look at from a distance, right? For example, climate change for a certain crop. Depends where you are, the footprint could be different. So looking at the picture as a whole might provide much more information for us, okay? So this project is setting up this model is very simple on paper, only has pretty much 4 steps. One is to delineate the model domain. The second one is to come up with areas of unique combination of soil texture, or soil property, I should say, topography, and land cover. So we do this as well. Those 2 steps have been concluded. I'm going to talk about this. The next steps will be parameterizing the model for specific crops, and then doing calibration and validation. When you do this at this scale, the challenge becomes data. Handling the data in itself is already a huge challenge. For example, for us here, we wanted to do some data screening to do what's the best data sets to use within each category. We are able to do this for soils. As you know, the Soil Landscape of Canada is a very coarse data set, 1 to 1 million scale. But there's also the detailed soil survey, which has much more detail. The idea for us is, does improving this type of representation in the model improve the simulations? Do I need that? How much precision do I gain by decreasing from a coarse scale to a much granular scale? We tried to do the same thing with digital elevation models. That was not possible because you can see the limitation of large scales. LiDAR is not available everywhere. So we had to mix those 2 together here. And for land use, we only have one access to the annual crop inventory. This is what you use. Because of the scale, again, we had to use very specialized tools that have to run in specialized environments. So this type of modeling does not run in consumer-grade computers, right? So it has to be in a high-performance computer. And even so, we have dedicated infrastructure for us here. We have 1,000 CPU cores to do this, and it still run into memory issues because the data sets are so large. So we had to sacrifice resolution here. We had to upscale the resolution to coarser data sets to be able to use this, because even those heavy muscle machines could not handle that. So this is the type of problems that you're dealing with. So this is the domain of the model from the first step, right? Watershed delineation. We end up with over 1,800 watersheds across southern Manitoba. So these are actual watersheds. They probably coincide with some watersheds that you see when you look at the conservation districts, for example, or watershed districts. So what you don't see on the map is the HRU definition piece, which is the unique combination of land use, topography, and soil, okay? So as you can see here, if I use the coarse soil data set, I have about 54,000 units to simulate. If I go for more detailed soils descriptions, I more than triple that. So this is the question I was asking before. Does this increase in representation here increase my output? Do I gain much on resolution of my outputs as I increase this? Because this has a computational cost, right? So if I try to run this, in this model, would probably take a couple of days to run. It's huge. So if I multiply this by 3, it's 3 times as much time. If I'm talking about hundreds, potentially thousands of simulations, you can see how much time this is going to take, right? To have time to do this. So I have to optimize this at this stage to be able to gain the best insights without sacrificing on, without having too much overhead in terms of computational steps. So the next step for this is actually going on into parameterizing the crops inside the model. So you're already approaching some of the commodity groups. They showed interest. As soon as I show this picture, you can see some eyes popping, right? Because they say, okay, I can do something with this. And so they have interest because now they can have a look at their industry at this scale, okay? How am I doing? So now I can prioritize areas. I can start looking at hotspots, cold spots, and things like this, right? So I can start looking at a different, so I have a meeting this week, have another one coming up as well, with some proposals and to discuss potential projects and moving forward with this. So this is something I'm really excited about. And the last study I'm going to talk about today is about biodiversity. As Kim likes to say, biodiversity is the new carbon. So people are paying attention to biodiversity, and we want to have been doing this work in Alberta and then replicating this in Saskatchewan. And the idea behind this is that agriculture land covers inside the agricultural, broad agricultural land use have a different impact on biodiversity. So because of natural grasslands, right? So natural areas. The beef industry utilizes those areas, so you want to compare, does the area utilized by beef, which is naturalized, have a different biodiversity footprint compared to another crop? This is the main question for us. So in order to do this, we got census data for the beef industry, and then based on this beef number, diets, consumption, and so forth, productivity of the land, we estimate the land use. Now we know how much of the landscape is used by beef. The second piece of this project was working with biodiversity database. The province of Saskatchewan has a database. It's not complete though, because they only have presence data in their database. So ideally, for using ecological models, you'd have presence and absence of the species. So it's not enough to record if the species is there. I have to record if the species is not there. This is something that people usually don't do. They just go and just look for what they can see, not for what they cannot see, right? But this model, Maxent model, they can handle that. So they use presence-only data, and then use the survey data together with the climate data. You can simulate the biodiversity footprint across the province. Here's the list of the weather data that we use in this analysis, plus some soil properties as well, because the ecology of some species are tied back to some soil properties. So include all that in the model. That was actually the heavy lifting of this exercise, was gathering this data set and pre-processing it. So this is just to show two independent data sets here. This is the land cover in Saskatchewan. You can see here native grasslands in green, annual cropland in brown, and then pasture in purple. And this is census data, right? So this is derived from census data and how much estimate of cattle grassland usage, which is based on animal numbers. So you see that whatever you have high number of animals is associated with specific land uses. So this is making the linkage between beef production and land use. This is where it becomes interesting. This is the compilation or the richness or relative richness. Remember I told you that we only have presence data, right? So because of that, you can only have relative richness. You cannot have richness because we're missing the absence. But this is a compilation of 260 plus species into one single map. So what was neat for us to see is that whenever you have annual cropping, you have light green to blue. That means lower biodiversity there. And for other areas where you have land uses associated with beef, such as grasslands and pastures, you have yellow, orange to red. That means higher diversity, right? One thing that you still have to figure out is this kind of artifact here. For example, we know this is grasslands. Why does it show such a low biodiversity? Okay? This could be due to low sampling in this area. So we're still assessing that, not sure about yet. So this was it in terms of scales, and hopefully my goal today was to make you think about the scales, not only on the work that we do, but also the work that you do, right? Because we tend to think about scales as something very static, but there's a lot of the effects on the scale in the work that you do at the field scale as well, because you can do micro, you can do field scale, you can do mesoscale. So hopefully I got you thinking about those aspects of our research that you do here. This is our team. So Nolan is responsible for the biodiversity modeling that you saw. Brian, they're all here, most of them. Brian was doing the grasslands assessment, also involved the hyperspectral. Bayan did the IFSM modeling with grasslands as well as the delineation of the watershed. Maria is working with the hyperspectral data, diving deep into all the models that you can create with that. And Victor was not in this picture. He's working on the SARI project in the corner here. And then decided today, our John, doctor, scans a lot. So that, he wanted to be in the picture, so we included there. So that was it. I'd like to also acknowledge the support, financial support from different people, different partners, different groups that have, believed in the work that you do here. This is not only Marcus. Besides this, is a bunch of people working together. People who collaborate across different departments here as well. So this is all part of what you're doing here. This is truly a multidisciplinary approach to the research that you do here. So Rob, with that, I'd like to conclude and be open to ask questions if you have any. Thank you.
Thank you very much, Marcos. Any questions? Yeah, Casey.
Definitely very interesting. For an individual farmer to implement this is probably quite expensive. So in order to get this growing, should it be commercialized? Or are there options for commercializing?
That's a good question. This is expensive in several fronts, right? I use the example of the drone because this is probably the most expensive example I can give. That sensor costs, the system costs hundreds of thousands of dollars. There's no way for a farmer to implement that. So the idea for us is to identify from the hundreds of bands that you have, the ones that are really telling the story for the farmer, and hopefully to come up with cheaper equipment or cheaper methodologies that they can implement, right? So on the modeling side as well, a lot of the modeling that we do here is open source as well. So we're happy to share the models with farmers that have interest. Actually, this is one important piece, is to try to do this engagement, right, the dissemination engagement with commodity groups to say, this is the work we did. How can you take this model and use it on your own farm? The biodiversity aspect is another one, right? We do it at the landscape level, but biodiversity is also important at the farm level. In each farm is a different universe. So we're trying to also pursue that route of doing biodiversity data collection at the farm and assessing that, linking that to management, because specific management will have specific outcome. So we want to look into that. So in terms of price, yes, what we're trying to do is to identify the best among all the options that the farm can implement, and hopefully can reduce the cost at that point.
Maybe
Sure.
Maybe related to the cost. You talked about AAFC.
Yes.
They seem to be a bit under siege, especially the plant and the final part of AAFC. To what extent is that a problem? Is the federal government in support of this?
Yes.
Especially financially.
It's very hard for me to speak for AFC, especially on the, because different branches and research stations were impacted different ways. But what I can tell is that the group that we work with out of Lethbridge, they are not impacted at the moment. So we're still able to continue with the modeling. They still continue the development of the model that we can still continue to collaborate with them. So they were not impacted. I agree with you, that's a hard to see kind of situation, but for us, was not directly, it didn't have any direct impact because of the people who collaborate were not affected.
But AFC in Saskatchewan, I think, that's...
They might have been. I'm not aware of the impact in Saskatchewan, but in Saskatchewan we're dealing mostly with USask. So researchers from the University of Saskatchewan.
Okay.
Yeah. Next case.
Yeah, I think USask research station is shut down.
Yeah,
The creators of canola, terrible. But on another Saskatchewan thing is I used to live on the other side of them, and if you look at a geographical map of Saskatchewan, that you claimed it was the U.S. influence. I think it's really slow. So it starts up in Cypress Hills and goes down.
Yes, yes. Because I think I wanna talk to Nolan to look at the species distribution, because this might be an artifact of the model. Because if there's not enough sample to work with, the model might just ignore that area. So we have to look at what's going on from a statistical perspective in the model, just looking under the hood and see what's going on there.
Okay, but I actually have another question about,
Okay.
This was based on your 28 systems and 8 systems, and you said if it was oilseed or cereals dominant, and I think if we look at the average acres in Manitoba, it's 1/3 oilseeds, 1/3 cereals, and 1/3 something else. And so, well, actually, I think sometimes a third is barley. It's like 1/3 canola, 1/3 wheat,
Yeah.
and 1/3 something else. When you say dominant, how big of the rotation was in?
Dominant within the rotation, not spatially. So the rotation was, let's say, wheat, canola, wheat, soybean. So the wheat will be the dominant crop in that rotation. It's not linked to spatial distribution of the crops.
Okay, the other thing is when you're saying perennial forages are high net zero, that perennial forage needs to be, needs a market, and it feeds into the beef sector, and you're not really doing the life cycle of the carbon if we don't figure out the emissions.
I'm glad you mentioned that. I mentioned this in our LEAP meeting last week. The whole point about perennialization is you have to keep in mind that livestock is an important piece, right? Right now, we're not modeling that. Actually, Kim and I are discussing the ways to integrate the livestock into the modeling. We're also discussing with other people in the group, like I think Michelle Korkner is thinking about using ruminants on their side in the plots as well. So without the livestock, you don't have a perennial system. You need that, right? So this is not showing this work yet, but for sure you bring it in because you need that cycle of that biomass through livestock to bring economical value to give you a destination as well, right?
I think Hollis can help you do that.
Yes, it does. It does. It's not in the model yet, but it will be there. Which can shift this balance, right? As soon as you bring livestock, the things can change. Yeah. The idea for us, I hope it's clear, is just to propose, if I'm going to propose changes to cropping systems, which type of change should I propose to where? This is our first step at looking at that. Yeah. Thanks, Sarah.
Joanne?
I have a follow-up question to that. So if we're going to include the ruminants or whatever livestock in the landscape when we're assessing the greenhouse gas emissions of a perennial forage-based system, can we also include the emissions for the livestock that eat the products from an annual system? How does that work?
This is where you have to draw your boundaries, right? No, LCAs are not perfect, never perfect. You have to make those decisions and draw the lines somewhere. So where to draw this line can be arbitrary. We try to support our decisions based on common sense and what's supposed to be. But if I keep increasing my system, eventually it becomes too complex to model. So this is the thing about large scales. As you increase the scale, you become more general. So you're losing the nuances. So that's why you go for averages, because you lose that little, detail here and there. But it's a matter of drawing a box. Where you draw a box, where your boundary. So I completely agree with you. I'm not sure at this point where you're going to draw that box yet, but we have to do it at some point. Thanks, John.
Other questions? Yes.
So this is for the drone system. So were you flying at a consistent height? How low were you going? And did things like a windy day or prop wash or anything like that influence how you use those pictures in your model?
Yes, we try to maximize. Can you guess how long that drone can fly?
5-10 minutes.
Yeah, you fly drones, right? Yeah, okay. So that drone can fly 6 minutes. So which is nothing. We thought you could fly much longer, right? So try to maximize this. So the way to do this is to fly as high as you can. So you fly at the ceiling that you can fly, 120 meters. So, and then you increase the swath. You're losing a little bit of resolution, but still your pixel size is still small enough, right? That you can still devise. Actually, we have hundreds of pixels for the quadrat that you saw that in the picture, people collecting samples have hundreds of pictures there. So how do I relate one crop sample, one value to 400 pixels? This is, have to average pixels. There's a lot of on the method side that you have to develop based on this. So we're also facing challenges on the LiDAR side. For example, the resolution of the LiDAR is 5 centimeters. Sometimes the vegetation is right within the noise of that sensor. So you cannot really pick on because you try to identify by combination of both hyperspectral and LiDAR, you try to get color and shape. What you cannot define based on color alone, the shape will help you, right? Is this vegetation lodging? How tall is it? So we can both together provide a lot of information. But there's some conditions under which even the sensor cannot get. If the vegetation is too short, you start getting to limitation of the technology itself, right? So if I want to jump from a high resolution, if I want to gain 2 centimeters resolution, go from 5 centimeters to 2, I jump from $20,000 to $80,000 sensor, okay? So this is that sweet spot, the balance I'm trying to find here, right? In terms of how much information do I gain with this much more expensive and detailed technology. So going back to, you're still trying to tease out, the idea for this, we didn't get that far yet to the question of seeing the effects of crops, not flying this on crops. It's just like uniform grasslands, mixed stand sometimes. The goal for us is to be able to go to the pigment level and identify species, okay? So we don't have samples for that, so I have to go back to the field, fly the drone and see. The image might show the difference, but now I have to sample those species. So I'm no ecologist, so I need now to find someone who knows grasslands that can, this is species A, this is species B, right? So we didn't get that far yet into separating that, it's just looking at the broad picture of the area, but the hope is that we go into looking at those more effects as discussed.
Okay.
Oh, you have your question?
Sure. Thanks, Marcos. Great presentation. I want to go back to that LEAP study very briefly.
Yeah.
And you looked at that soil regarding carbon and scaled the various systems or classified the various systems in soil regarding carbon. I can't remember what the magic equation was, but the pulse-dominated systems looked the worst, right?
To some
They were the brightest red, if I got that right.
That's,
And if they are,
let's see here, you can see this.
oh, right there. Okay. Yeah, the pulse ones look the worst. Why is that? We tend to associate pulse crops with fixing nitrogen, lower carbon.
Good question. Yes. So the one thing that Holos is very, very, very sensitive to is yields. Okay? So right now, I didn't mention this, but we are taking a coarse approach here, using regional values of yields. Okay? So the next step, the second tier for us would be to use farm yield levels. So hopefully we'll be able to, this might shift a little bit. So based on publicly available data from mass database and stuff like that, this is what you got. But if you go back to the farm level, which through the LEAP project we have access to the records, now we can go back and fine tune this. So I cannot tell at this moment because it's still fresh to say specifically why that is. But my guess at this moment is this is probably guided by yields.
I think, is Yvonne here? I think what she told me when I was looking at trade-offs and binoculars with this is that in soybeans, there's very little carbon left in the soil after a soybean crop. So this part of the pulses, that could be what's taken.
As you can see there, I don't have the pointer here, but you can see the pulse is about halfway on the emissions, just under halfway the storage, right? The soil carbon. As you said, the question now is how much potential there is here to drag this point to the left and then up. For some of them, there's no hope to move up, right? The only hope is to move left and right, or hopefully left. So this is why we're discussing that the intermediate systems could offer some hope here because now we have two levers, right? One on the emission, one on the soil carbon. So can I maximize soil carbon while minimizing emissions? So this might mean shifting a larger proportion of the cropping system of the rotation into perennials as opposed to, right? So I might need to make hard decisions based on this. And as you saw here, it depends on wet conditions too. So if you look at probability of extremes, is it drier, is it wetter, is it both? So how would these systems behave under those conditions? So this is not the full picture yet. I still have to look at climate into this as well, which you could probably run into Holos as well. Just get climate projections and run this. So this is right now a sandbox for us. So we still have to dive a little deeper and see. You welcome any inputs that you guys might have to discuss this, right? So question well taken.
Excellent questions, everyone. I really appreciate the conversation and discussion. Other questions? Casey?
What's the potential financial benefit of a farmer to participate? Do you see subsidies at some point?
So as you can probably tell, Case, at the level we're working with, you're working at the commodity level here, right? Not at the farm level per se. You could probably try to dive in, but the thing is, the commodity group is thinking about messaging, for example, right? In terms of how environmentally friendly my crop is, for example. This can help that kind of idea. If you wanted to look at your farm, if you're talking about carbon credits, for example, this will not do it, right? This has to be done at your farm with a lot of monitoring, very specific monitoring. So if you want to go down to the farm level from here, you have to do either modeling at that level or do measurements and doing other approaches as well. This doesn't preclude you from doing this. This might actually give you pointers in terms of hotspots. For example, oh, my farm is, for example, in risk area 8, right? I have a corn farm in risk area 8. What does it mean in terms of potential for droughts or potential for climate change impact on my yields or impact of emissions, for example? So at that level, we have to go to a different level of modeling as well and monitoring. Might need more monitoring than modeling, I should say. Does it make sense?
Yes.
Yeah.
I mean, personally, the dairy industry reducing methane is a very big thing. But when farmers do not see a financial benefit,
Yes.
it won't be happening.
There is a very good example because the IFSM model discussed is very fine-tuned for dairy. So we just published a paper end of last year about modeling a dairy farm in BC, a very intensive dairy farm in BC. So for that type of assessment, there are specific tools that you can use. IFSM is one of them. So we can do very precise, and it takes in consideration the animal aspect, the crop aspect, the soil aspect. It's really a farm model. So you can do a lot with that, but it would not be of the level of detail, coarse detail that you discussed today.
Excellent. Thank you, everyone. I think we're out of time. Wonderful discussion. Thank you so much, Marcos. Let's thank Marcos one more time. Thank you, everyone, for coming, and look forward to seeing you at the next faculty seminar. Thank you. Have a good evening.